Okay, so now we're going to carry on. We're now going to finally think about how to use path integrals in quantum field theory. So this is section 2, path integrals in free quantum field theory. Okay, so you studied the basic ideas of quantum field theory in IFT, so let me just remind you. We're going to begin with a free scalar field phi. So what is the action of the scalar field? Remember, phi is a function of x, which is shorthand for a field which depends both on space and on time. And the action of the scalar field phi, I'm going to write like this. S of phi is a functional, which you write in the following way. Integrate over all of the spatial and time coordinates. And the action looks like this. Okay, there's a kinetic term and a mass term. Now, of course, you're familiar with this action already. One thing that you can do is you can integrate by parts on the kinetic term and write it in the following way. Like this, okay? And this form is going to be a little bit more useful in what we're going to do. So now, what are the classical equations of motion from varying this action? If you vary the action, what you find is that the classical equations of motion are just partial squared plus m squared phi equals to 0. That's pretty much immediate from this equation right here. So next what we want to do is we want to use path integral methods to develop the quantum field theory, the quantum theory associated with this Lagrangian. So this is actually philosophically the same as the quantum mechanics problem. So let me just try to explain that a little bit more. You've already understood how in quantum mechanics to go from QFT and put this into a path integral. Now, it shouldn't be too hard to understand how you could do this for, say, a vector, q sub a of t, where a runs over, let's say a runs from 1 to n, so q is now an n-component vector. It should be pretty clear how you would do the path integral over this vector field. Over this vector quantum mechanical system, right? Okay, good. So now, just imagine that what we do is, imagine that A, instead of running from 1 to n, imagine that A runs over the sides of a lattice. Okay, so I have a spatial lattice, and A runs over the sides of a spatial lattice. Okay, so here's some sort of spatial lattice. Okay, now this lattice goes on forever, so the n is a very, very large number here. But that's okay, right? There's no philosophical problem. And now you can see that because A essentially runs over spatial points, this is pretty much the same thing as having a field which depends on space and on time. The role played by this index A is actually now played by space. Okay? So this is a little bit formal, but the main point is that everything you've done for quantum mechanics, you can take over without too much worries to do field theory, to do quantum field theory. One thing that is kind of important is that, you see, there is a lattice spacing in this lattice here. There's some sort of size, delta here. And you might worry that, I took this n to be infinite. Is this going to cause a problem? Is there something slightly subtle happening as you go from having a discrete parameter a to a continuous spatial parameter x? And that is actually true. You have to worry about that. And we're going to return back to that later. But for now, let's just carry on. Okay. So the main point is you can define a path integral in precisely the same way that you do for quantum mechanics. You can define a number z, which is just integrate over d phi, exponential of I s of phi, where this now is the functional integral over functions of space and time. Okay. Okay, good. So this object z here, this generating functional, is basically what we're going to study for the rest of this course. So there are two main things that are nice about doing quantum field theory from path integrals in this way. And one of them is honest and the other one is a little bit secret. So let me tell you what the advantages are to path integral quantum field theory as opposed to, say, normal canonical methods, the ones you've learned already. So why path integrals? The first choice, the honest one, there's an honest reason. The honest one is that all the symmetries are manifest. So what do I mean by this? When you do canonical methods, for example, in IFT, you have to pick a time slice, right? You pick some coordinate t, and you do canonical methods with respect to that coordinate t, that choice of time. Okay. This breaks Lorentz invariance because Lorentz invariance mixes space and time. So in a sense, Lorentz invariance is broken, and at the end of the day, all of your answers are Lorentz invariant. But it was kind of not obvious, right? There's some peculiar cancellations that happen. Your answers are Lorentz invariant, but the intermediate steps in the calculation aren't Lorentz invariant. So it always kind of seems like a miracle when your final answer is indeed Lorentz invariant. This won't be the case here. Lorentz invariance is going to be manifest all the way through the calculation, and that's kind of nice if that's something that you want to preserve. Okay, this is an honest reason. There's a sort of a bit of a more secret reason, and the secret reason is that the path integral makes gauge fields easier, and the reason why is that it lets you be a bit more sloppy about subtle issues like, what is the Hilbert space really? And this is nice because this question in gauge theory, as we'll see, is a little bit complicated. If you're curious about this, Google the words Dirac bracket and you'll see all the many things that can happen. The nice thing about path integrals is that they let you quantize a gauge field without working too hard. Okay? So that's another reason why path integrals are typically how gauge fields are taught, at least at first. Okay, so let's carry on. So next up, let's do a calculation. So I'm going to try to develop some of the machinery here. Let's calculate the 2-point function. And we'll do that by digging a little bit into this generating functional. So what I want to do is calculate the following 2-point function. I want to calculate the time-ordered correlation function of 5x, 5y, using path integrals. Okay, you already calculated this in canonical methods. We're going to do it again now using path integrals. So, by the way, this object is called the Feynman propagator. It's very important for lots of different reasons. It's basically the building block of how we do perturbation theory. But for now, let's not worry about that. Let's just calculate it. Okay. So by arguments which are pretty much the same, let me just define this as ... for simplicity. So by arguments which are pretty much the same as those in quantum mechanics, you can calculate this in the following way. It's equal to 1 over z0 times the integral of d phi 5x 5y times the exponential of is of phi. And this is just like in quantum mechanics. Okay, the arguments leading to this are precisely those that appeared in quantum mechanics. Now, to calculate this, it's good to define the same generating functional as we did in quantum mechanics. So I'm going to define a slight generalization of what I had on the previous slide. Z of j is defined to be the integral d phi, the exponential is of phi, plus I integrate d4x, j of x, 5x. Excuse me, I seem to have run out of board space. So now we again do the same sort of thing that we did previously in the quantum mechanical setting. In particular, it's fairly easy to see that this thing here is given in the following way. I can calculate this by taking the following functional derivatives. I take 1 over z naught. Okay. So in other words, I take a functional derivative with respect to j, which brings down a phi of x, and I take a functional derivative with respect to j of y, and that brings down a phi of y. All right. Okay. So now we just have to evaluate this. So let's do that. To do that, it is helpful to remember an identity for doing Gaussian integrals. Let me remind you how to do Gaussian integrals. So again, you should have seen this in QFT1, but if you don't remember, that's okay. Take a look at the homework for this week. In particular, write this down carefully. So here, x is a vector living in Rn, and I'm integrating over all of the n components of x. All right. And here there's a matrix A and a linear term j. And you can show straightforwardly that the following thing turns out to be this. Determinant of A times the exponential minus half JA, A inverse AB JB. Okay. Now, again, I think you've seen this already. This is sort of just straightforward just manipulation of finite dimensional integrals. If you've not seen it, take a look at the homework for this week and you can derive this formula for yourself. It should seem plausible. Now, the point is, this is true for a finite dimensional integral, but as physicists, we're just going to brutally, boldly just use this for our infinite dimensional case. Okay. In particular, if you look at the form of the action, let me go back and show you the action. If you look at the form of the action takes the same form as what I just described, in that there's a quadratic operator, which is sort of like A, in between two things that we're integrating. Okay? So, therefore, the analogy here is that to apply this to our case, it's pretty much exactly the same, except that the operator A is this differential operator, d squared plus m squared. So, therefore, the answer to our functional integral z of j is, here we go, it is the determinant of the thing that's like A, so in other words, d squared plus m squared. I'm being careful about factors of 2 pi I times the exponential. Again, over here, we sum over little a, which sums over all the indices. Those sums are replaced by spatial integrals. And so we just get d4x, d4y, j of x, second. Okay. So I hope it's clear what's happened here. What used to be a sum over the components of this vector is now an integral. Okay. And j of x and j of y play the same role as ja and jb. And df here plays the role of a inverse. Okay. So let me write that down because it's important. df plays the role of A inverse. It's just a name. But to tell you what that means, that df plays the role of A inverse, I should tell you what df is defined as. In that formula, df is defined in the following way. It's the inverse of A, which means that when A acts on it, you get the identity. Oh, sorry. Okay, this equation here is the definition of df. Okay, good. So that defines df. Let me go back to this expression here. So there's a couple of things to digest here. So first of all, let's note that the path integral is asking us to compute the determinant of a differential operator. This is, you might wonder, what is that? What is the determinant of a differential operator? So the way to calculate this is what you do is the same thing you always do when you compute a determinant. The determinant is actually the product of the eigenvalues. So what you do is you find the eigenvalues of the differential operator and multiply them all together. So this is really a very beautiful thing. Again, take a look at the homework where you'll get to mess around with this a little bit. But we're not actually going to need it much in this thing, so we'll come back to it later. Now, the next thing to note is the dependence of this object on J is actually very simple. It's the exponential of a quadratic. And recall that what we're trying to do is we are trying to compute Z as a function of J so that we can take functional derivatives of it to get the two-point function. So given that, it's very easy to do this. So if I call this equation star, let me now take functional derivatives of equation star. And if you do that, it's easy to see that the time-ordered correlation function turns out to be exactly dfxy, where df is defined above. Okay? And again, this comes from equation star as well as this equation right here. Okay, if that wasn't clear, I encourage you to pause this. I believe the pause button is here, and take a step back and stare at the calculation. Okay, you're back. Good. So that means this all makes sense. So now let's carry on. Let's actually calculate this. All right. And finally, by the way, you should have seen this already. I think that in IFT you have again already seen this, that the time-ordered correlation of phi is equal to the Feynman propagator. But let's actually calculate it and do it in sort of the path integral way. Okay, so next up, on to section 2.2. In section 2.2, I'm now going to calculate the Feynman propagator. Okay, so here we go. Let's actually calculate this object. The first thing we're going to do is we're going to go to Fourier space. Okay, so why are we going to do that? Well, we're going to do that because it makes the answer easier. But in general, it's important to note that our problem has translational invariance. In general, whenever you have translational invariance, it's probably good to go to Fourier space if you're trying to solve a problem. That's something to keep in mind. Okay, in Fourier space, the Feynman propagator looks like this. So all I'm doing here is defining the Feynman propagator. Okay, so df twiddle is a function of p, which is a four momentum. And our task is to determine this function df of p. So what we do is take this form, okay, so take this decomposition and insert that decomposition into this definition right here, the definition of the Feynman propagator. Now what happens? Well, the point is that the derivative here, when acting on the Fourier transform, brings down a factor of p squared. So in other words, this differential equation becomes the following thing. So again, I am just sticking this into there. p. This equals 2 minus I delta 4 x minus y. Okay. Okay. So let's think about this. It seems that there's this useful identity. Okay, so recall the following useful identity. The integral of d4p e to the ipx is 2 pi to the 4th delta 4 of x. So this is a useful identity. We sort of want to use that. So you can see that if df twiddle of p is 1 over p squared minus m squared, then these two bits will cancel and we can then use this identity, excuse me. Okay? So if we so that tells us what df of p is. It must be 1 over p squared minus m squared. If you get all the factors right, it turns out it's a factor of I. And we end up with the following expression for the propagator in Fourier space. Df twiddle of p is I over p squared minus m squared. This is an extremely important formula. This is the Feynman propagator in momentum space. And we'll use this over and over again in what follows. Okay, so this looks nice, but actually it's not done yet. The point is, specifying this Fourier transform does not yet completely specify a function in position space. Okay, so why is that? So to understand this ambiguity, which I claim there is, let's try to Fourier transform this back. Okay, let's try to Fourier transform back. All right. So let me break up, in other words, let me compute the integral over p, okay, over d4p, the integral over here. But to do that, let me first break up p mu into a, p lower mu. Let me first break up p mu into a p0 and a spatial momentum. And let me also define the following quantity. I'm going to define omega sub p to be the square root of p squared plus m squared. And finally, I'm going to do the time integral first. Okay. So given all these definitions, let me first write out the integral. I have the df of x and y. dp0 2 pi d3p 2 pi cubed. Now here I'm just plugging in the value of df twiddle of p. It's p naught squared minus p vector squared. P naught squared minus p vector squared minus m squared. And finally, there's something in the exponent. The exponent was e to the I p dot x, which if you write out carefully turns out to be e to the I p naught x naught minus y naught I p x minus y. Okay, so that's fine. Let me now expand this quantity out a little bit, okay? And I'll do that on the next slide. So I'm going to expand this part out. What I get is that this thing is I times the integral of dp naught over 2 pi d3p over 2 pi cubed. P e to the minus I p naught minus y. Okay, so now what's happening here? So what I just did was, just to be clear, What I did was I just expanded this thing out. You can multiply together these two products and you're going to get p squared minus omega p squared, which is, of course, just exactly what's here in the denominator. Okay, so now look at what's happening here. In the integral, there are poles when p naught equals to plus or minus omega p. This is confusing because I'm trying to integrate over all p naught. So in other words, I get divergences when p naught hits omega p. So the correct way to think about this is the following. I am doing an integral over real p naught, but let's consider instead the complex p naught plane. There is a pole here at plus omega p and a pole here at minus omega p. To actually do the integral is trying to tell me to just go through this thing here. Excuse me, the integral is trying to tell me to just do an integral through that right there, except just to go all the way through this. But that doesn't actually make any sense because then I'm going to hit the poles. So in other words, to make this integral well defined, what I actually need is a prescription on how to go around the poles in the complex p naught plane. Okay, so for example, I could go like that, I could go like that, I could go like this. These will all give slightly different answers, and I need to know how to do that. Okay, so let's take a step back and think about this for a second. So there's various things that we want. So first, let's note that number one, let's take x naught minus y naught to be greater than 0. Okay? If x naught minus y naught is greater than 0, then what we have to do is, when we do this integral, we have to complete the contour below for the integral to converge. Okay? In other words, whatever complex analysis mumbo jumbo I do, no matter what, I have to complete the integral below. Okay? Because otherwise, this guy right here, this exponential, is going to blow up. So I have to complete integral below. Okay. However, there are still multiple ways to go around this. So to get the second bit of information that we need, I want you to remember something that I said way at the beginning of this lecture, a million years ago, which is the following. Recall that the path integrals make sense. So path integrals are well defined only if we formulate them in Euclidean signature. Let's recall what that means. Remember the Wick rotation? So the Wick rotation was what we did to go from real time to imaginary time. In particular, that also acts on p naught because p naught is the momentum conjugate to t. So in other words, I can go from real p naught to Euclidean p naught. Okay. But in other words, what that means is that the integral was really happening up and down in the complex frequency plane, in the p naught plane. In other words, the integral happens on the imaginary p naught axis. This tells us the way to complete these poles. So in other words, what I have to do is, I have to do my initial integral along the imaginary p naught axis, and then I have to complete the integral below, which means that I end up here. Okay. So perhaps the better way to say this is that when I was saying that I was integrating over real P naught, in reality I was integrating like this, because this is the contour that can be continuously deformed to be up and down on this axis right here. Okay. So again, I hope that made sense. But just to tell you, this information that we're coming from Euclidean signature tells us how to do the integral, because only one pole prescription is compatible with this. Okay, so now we can do the integral. We do this with complex analysis. So what we do is we write down the df of x and y equals 2. So what we do is we go this way and we circle the pole in this manner. And we take the contribution from the plus omega p if x naught minus y naught is greater than 0. So what I then find is there's a minus 2 pi I coming from the fact that I'm circling a pole, but I'm doing it the other way. That 2 pi was in the answer to begin with. The d3p goes along for the ride. And now the whole thing is multiplied by the residue in the p naught integral. What is the residue? If we go back and look at this, what's happening is I'm picking up the pole from here. To get the residue, I just sort of drop this factor and keep everything else, but I set p naught equal to omega p. So what that means is I get 1 over 2 omega p e to the minus I omega p x naught minus y naught plus ip x minus y. And this is the answer if x naught is greater than y naught. Okay. Okay. That was a little bit of machinery, so I'll give you a second to pause if you'd like and take a look at it again. Now, similarly, if x naught is less than y naught, then we close the integral the other way. Okay, then you have to close the contour above. And you then end up picking the residue from p naught equals to minus omega p. And the answer you get is df of x minus x and y equals 2. At this point, you get 2 pi I times I divided by 2 pi integral d3p 2 pi cubed. Here we have a minus 2 omega p. And you have e to the I plus omega p x naught minus y naught plus ip x minus y. Okay, so you can see this is pretty much the same thing with a few crucial signs that are a little bit different. Okay, that's it. We have done the hard work of calculating the time-ordered correlation function, also known as the Feynman propagator. There's one more integral to do. There's an integral over d3p. This is totally doable, but it involves a little bit of messing around with Bessel functions. I don't want to do it in real time, but I might assign it as a homework. So finally, let me say that there's a convenient way to summarize this business with the pole. Okay? And this whole business with the pole is often written in the following way. df twiddle of p is I over p squared minus m squared plus I epsilon. This I epsilon is telling you how to tip the contour up, okay, to get this thing. This is often called the Feynman prescription, and it just sort of is a convenient way to summarize this whole jumping around in between Euclidean and so on that I just described. Okay, so the epsilon is some infinitesimal which is positive, which will tell you how to tip the contour upwards. So let me just summarize this. The point is, path integrals give us time-ordered correlation functions. Okay, and if ever you're confused about how to go around a pole, you should remember that the path integral was secretly defined in Euclidean signature. This typically helps tell you what to do. Okay, so we are almost done with this brief introduction. So just one more thing that I want to talk about today, which is higher point functions. This is section 2.3, and this is higher point functions in the free theory. So, we just discussed how to compute a two-point function, but you can use the same ideas to compute higher point functions. So for example, suppose you want the following. Suppose you want to compute the time-ordered correlation function of phi of x1, phi of x2, phi of x3, and phi of x4. Okay, so you want to compute this object. So, just like before, what we do is we just take multiple functional derivatives of z of j. Previously, we took 2. This time, we will take several. Okay, so, oh, sorry, I left out something crucial here. Excuse me, write this in the following way. So this product runs from 1 to 4, and we have a minus I to the 4th, 1 over z naught. Now, again, this is a completely straightforward thing to do, which I'll leave you to work out. The main point is, because z of j is a Gaussian in j, the resulting answer from performing this manipulation is just different combinations of df of x and y. Okay? So for example, you can work this out for yourself. This thing right here turns out to be minus I to the 4th times, here we go, df of between x1 and x2 times df between x3 and x4. Plus, let me abbreviate my notation a little bit. It should be clear what I'm saying. Between x1 and x3 plus df times 2 and 4 plus df between 1 and 4 times df between 2 and 3. Okay? So in other words, what you're really doing is you're drawing propagators between all different pairs of points. Okay? Because this is going to be really important, let me draw a little picture for this. So if I have, for example, x1 and x2, and here I have x3 and x4, the first term was between 1 and 2 and between 3 and 4. The second term was between 1 and 3 and 2 and 4. The third term was between 1 and 4 and 2 and 3. Okay, I left out the 2 and the 4 here. So it should be clear if you work through this example and think about what's going on. This will work for any number of insertions. This fact is called Wick's theorem. Okay, and Wick's theorem is just saying that if you have a Gaussian here, if you have a Gaussian theory, then all the information is contained in the two-point functions. So that concludes lecture 1. From the next lecture, we're going to take it off and work on interacting theories.